Antimatter, the flip side of reality. Space is vast. It's full of mysteries, enigmas that have puzzled humanity for centuries. Black holes, distant galaxies, and things we haven't even imagined yet. The cosmos is a treasure trove of the unknown. But one of the most intriguing puzzles lies not in the depths of space, but in the heart of matter itself, antimatter. This elusive substance challenges our understanding of the universe. It's the flip side of our reality, a mirror image of the particles that make up everything we know. Imagine particles that are identical yet opposite in charge. Imagine a world where everything is the opposite, a place where the rules of physics as we know them are turned upside down. Up is down, left is right, and matter is antimatter. This concept stretches the boundaries of our imagination. This isn't just science fiction, it's a tangible reality that scientists are exploring every day. Antimatter is real, and it's stranger than anything we could dream up. Its properties defy conventional logic, but here's the catch. Antimatter is incredibly rare and incredibly expensive. The cost of producing even a tiny amount is astronomical. We're talking billions of dollars per gram. This makes antimatter one of the most precious substances known to humanity. Why? Because creating and storing it is a monumental scientific challenge. The process requires cutting-edge technology and immense precision. In this exploration of antimatter, we'll journey into the subatomic realm, unraveling the mysteries of this elusive substance. We'll see how it interacts with matter and the potential it holds. We'll delve into its history, its mind-boggling price tag, and the groundbreaking research that has brought us to where we are today, and its potential to revolutionize our world. From energy production to medical advancements, the possibilities are endless. Fasten your seatbelts because the universe of antimatter is about to get real. Join us as we uncover the secrets of this fascinating frontier. Mirrors and opposites. Understanding antimatter. To understand antimatter, let's start with what we know, matter. Everything around us, from the chair you're sitting on to the stars in the sky, is made up of tiny particles called atoms. Atoms have a nucleus, containing protons, positively charged, and neutrons, no charge, orbited by electrons, negatively charged. Antimatter is like matter's mirror image. For every particle of matter, there's an antiparticle with the opposite charge. A proton has a negative twin called an antiproton. An electron, a positron, its positively charged counterpart. When matter and antimatter meet, they annihilate each other in a burst of pure energy. It's the ultimate demonstration of Einstein's famous equation, E equals mc squared, where a small amount of mass converts into a tremendous amount of energy. This energy release is what makes antimatter so powerful and so potentially dangerous. Imagine the energy of the sun compressed into a space smaller than an atom. That's the power of antimatter. From equations to existence, a history of antimatter. The story of antimatter begins not in a lab, but on paper. It was a theoretical concept before it became a physical reality. In 1928, physicist Paul Dirac was working on equations to describe the behavior of electrons. His work was groundbreaking and would change our understanding of the universe. His equations predicted something incredible, a particle identical to the electron but with a positive charge. This was the first hint of antimatter. At first, Dirac hesitated. Could this anti-electron really exist? It sounded like science fiction. The idea was so radical that it challenged the very foundations of physics. But in 1932, the unthinkable was confirmed. The theoretical became real. American physicist Carl Anderson discovered the positron in cosmic rays, high-energy particles that bombard Earth from space. This was a monumental discovery. This discovery was a watershed moment, proving that antimatter was not just a mathematical quirk, but a fundamental part of our universe. It opened up new avenues of research and exploration. Since then, scientists have created antiprotons, antineutrons, and even antihydrogen atoms, the antimatter counterpart of hydrogen. These achievements have expanded our understanding of the universe. The discovery of antimatter opened up a Pandora's box of questions. It challenged our understanding of physics and the universe. If matter and antimatter annihilate each other, why is there any matter left in the universe? This question has puzzled scientists for decades. Where did all the antimatter go? This mystery remains one of the biggest unsolved questions in physics. These questions continue to baffle physicists today and fuel our quest to understand the origins of the cosmos. The search for answers drives scientific inquiry and exploration, pushing the boundaries of what we know. The astronomical price of antimatter. Antimatter is often touted as the most expensive substance on Earth, and with good reason. Producing even the tiniest amount requires immense energy and sophisticated technology. Current estimates put the cost of producing 1 gram of antimatter at over $62 trillion US. Why so pricey? The main culprit is the energy required. Creating antimatter involves smashing particles together at near light speeds in particle accelerators, massive machines that consume enormous amounts of power. Think of it like trying to smash 2 eggs together so hard that they create a whole new kind of omelet, except the eggs are moving at nearly the speed of light, and the omelet is antimatter. It's a highly inefficient process with only a tiny fraction of the energy converted into actual antimatter. Then there's the challenge of storage. Because antimatter annihilates on contact with matter, it can't be stored in a regular container. Scientists use magnetic traps to suspend antimatter particles, preventing them from touching the container walls. These traps are complex and require their own energy supply, adding to the overall cost. The infrastructure needed to produce and store antimatter is incredibly sophisticated and expensive. Highly trained scientists and engineers are required to operate and maintain these systems, further driving up costs. Antimatter is not just a scientific curiosity, it has potential applications in fields like medicine and energy. For instance, positron emission tomography, PT, scans use antimatter to help diagnose diseases. In the future, antimatter could even be used as a highly efficient fuel for space travel. Imagine spacecraft powered by antimatter, capable of reaching distant planets in a fraction of the time it takes today. Despite the astronomical costs, research into antimatter continues, driven by its incredible potential. As technology advances, the hope is that one day the production and storage of antimatter will become more feasible and less costly. Until then, antimatter remains one of the most fascinating and expensive substances known to humanity.